इंट्रिंसिक कैरियर कॉन्सेंट्रेशन. ओके, इसको Ni से हम रिप्रेजेंट करते हैं. And also intrinsic semiconductors are electrically neutral. Electrically neutral का क्या मतलब है? They are not charged. The total number of electrons are equal to the total number of positive charges, okay, including the holes. So they are electrically neutral. इसको हम कहते हैं electrically neutral. So these are some terms which come in some of your objective questions, so we should be able to link with that. Intrinsic semiconductors are electrically neutral means that it is not charged, because total number of positive charge is equal to the total number of negative charge out here. Okay, now talking about what happens and how the electrons they move. Semiconductors, as I have written here, I have stressed on this point here, they possess the unique property that apart from electrons, the holes can also move. So that's one important difference what we have here. So suppose that you have a hole at some site, let's say site 1 है और site 1 में यहाँ पे hole था. So movement of holes can be visualized as shown here. This electron finds that the grass on the other side is green. So it will go to the other hole here, fill up this hole, and that will leave a hole in the original position. So movement of bound electrons is actually equivalent to movement of holes in the opposite direction. All right. So that's what we are writing here. An electron from the covalent bond from site 2 may jump to the vacant site. And after that jump, the hole is now at the new site. And site 1 is now having the electron. And apparently it appears as if the hole has moved from site 1 to site 2. And the electron which was originally set free, that is from here, that has no role to do in this whole process. That's another thing. Like some students may think that maybe the electron which was free, that has something to do with this movement. So we are again stressing here that has nothing to do with that whole thing. वो तो free हो गया और वो चला भी गया है. Okay, till here this is also fine. श्रेया, ये जो हम बात कर रहे हैं ये है जनरेशन ऑफ इलेक्ट्रॉन होल पेयर्स. अभी तक हम बात कर रहे हैं जनरेशन ऑफ इलेक्ट्रॉन होल पेयर्स. इसको ऐसा लिखा जाता है. बट जनरेशन के साथ अभी हम देखने वाले हैं कि रिकॉम्बिनेशन भी होगा, क्योंकि जो इलेक्ट्रॉन वैलेंस बैंड से कंडक्शन बैंड में जाता है वो परमानेंट नहीं है. वो ऐसे नहीं कि वहां पे जाके वो बंगला बांध के उधर रहेगा, बिल्कुल नहीं. वो थोड़े देर ही रहेगा, वापस वो वैलेंस बैंड में आ जाएगा. इट इज गोइंग टू कम बैक डाउन. सो along with generation of electron hole pairs, there is going to be recombination of electron hole pairs also happening. So let's talk about that. Okay, so जो free electron है, okay, I don't know whether this slide is talking about that. Let's see here. The free electron जो है, it's free to move under the influence of an electric field. तो अगर आपने electric field लगा दिया तो electrons will move in a direction opposite to the electric field, and that will constitute the electron current, IE, जो हमने यहाँ पे लिखा है. So what the statement is saying that in semiconductors the total current is a combination of electron current and hole current. So electrons, they will move in a direction opposite to the direction of the electric field if you establish an electric field. Okay, and motion of holes is actually motion of bound electrons. Okay, so this bound is very important. Motion of hole is not motion of free electrons. It's motion of the bound electrons. And under the action of an electric field, these holes, like positive charges, will be moving in a direction of the negative potential, lower potential में जाएंगे. क्योंकि positive charge है, तो positive charge will be pushed in the direction opposite, in the direction of electric field में जाएंगे. So they will constitute a hole current. So if you have an electric field out in this direction, then your electrons are going to move in a direction opposite to the electric field, and the holes are going to move in a direction of the electric field. So this is going to be the total current in semiconductors. Acceptable, Mohit? Okay. So as I told some time back, I have spoken about process of generation. And what type of generation is this? This is called as thermal generation. Because of sufficient energy which you are getting at room temperature, उसके कारण ये thermal generation हो रहा है. But simultaneously, you also have to discuss the process of recombination, where an electron will recombine with the hole. And why that happens? As I told you, that the electrons which are shifted to the conduction band are not going to make a bungalow there. The typical lifetime is going to be around 10 raised to minus 8 seconds. उतना ही टाइम वहां रहेगा, फिर नीचे आ जाएगा. Okay, so when you talk about equilibrium, so हम लोग in force we used to talk about equilibrium. Same thing here also we say equilibrium. Equilibrium का मतलब है rate of generation of electron hole pairs is going to be equal to the rate of recombination of the carriers. Correct. So this process, that particular state is called as a state of equilibrium. So the number of electron hole pairs are going to be continuously generated, and then and the electron hole pairs are also going to keep recombining all the time. And when these two rates become equal, we say that the semiconductor is in equilibrium. Or that is from the energy level perspective. From the perspective of your bonds, you can say that probably the electron is colliding with the hole. So there is a hole, and the electron which was free comes and collides with the hole and fills up that hole. So that's how the holes are also going to be filled up by the electrons. All right. So this process of generation and recombination equilibrium is also clear. Omkar? Okay. Now going up here, this is the state at 0 Kelvin. Okay. So 0 Kelvin mein you can see that the valence band is completely filled up and the conduction band is completely empty. तो 0 Kelvin के लिए ये diagram draw किया गया है. So when the temperature is 0 Kelvin, then there is no energy available for these valence electrons to overcome this band gap and come here. But when the temperature increases, so if temperature is greater than 0 Kelvin, we have this diagram, where some of the electrons will overcome this band gap and come here and become holes here. So these are your holes and these are your free electrons and these are your bound electrons. And further, these electrons will also come and recombine with the holes. All right. So this is one diagram which is summarizing all those points there. So we represent the holes with a circle and we represent the electrons with a blackened circle in general. All right. So I hope we can go ahead. So here, this is actually one small example from your CBSE book, but one important point which I found out here, and that's why I was thinking I'll discuss it here. So at the beginning only, I had shown that electronic configuration for carbon, silicon, and germanium. And the question here is that why is carbon an insulator and why silicon and germanium are intrinsic semiconductors? They have asked that question. Okay, so of course, you know from the viewpoint of band gap diagram that कार्बन का जो बैंड गैप रहेगा ये बहुत ज्यादा रहेगा और सिलिकॉन और जर्मेनियम का कम रहेगा. मगर एक और बात है कि सिलिकॉन और जर्मेनियम का भी अगर आप कंपेयर करोगे बैंड डायग्राम्स, बैंड गैप एनर्जीज ये अलग अलग है. इट इज नॉट द सेम बैंड गैप. सो व्हाट इज द रीजन फॉर दैट? एक्चुअली कल हम लोग जब मॉडर्न फिजिक्स करने वाले हैं, सो वी विल बी टॉकिंग अबाउट व्हाट इज द एनर्जी लेवल ऑफ द डिस्क्रीट एटम का जो एनर्जी लेवल होगा, it depends on what, and we'll be deriving the relation that the energy level will be inversely proportional to 1 by n square, where n stands for the principal quantum number. Okay, so that derivation we will be reserving it for modern physics tomorrow. We'll be dealing with it, principal quantum number. So if you remember, I had told some time back that carbon में जो outermost shell है ये second वाला होता है, और जो सिलिकॉन में है ये थर्ड है, और जर्मेनियम में ये फोर्थ है. तो इनमें से अगर आप देखोगे ये क्या है, ये एनर्जी लेवल ऑफ द ग्राउंड स्टेट है, एनर्जी लेवल ऑफ द ग्राउंड स्टेट ऑफ अ पर्टिकुलर एटम. तो इनमें से कौन से एलिमेंट का ग्राउंड स्टेट का एनर्जी लेवल सबसे कम होगा? If I'm giving you this relation, I don't know whether you are aware of that relation, but if you presume that relation is true for the moment, which will prove tomorrow, then कौन से एलिमेंट का एनर्जी लेवल इन द ग्राउंड स्टेट कम सबसे कम होगा? ये इनवर्सली प्रोपोर्शनल टू n स्क्वायर है. यहां पे देखो 4, 3 और 2. जर्मेनियम, करेक्ट. जर्मेनियम का देखो n सबसे ज्यादा है, तो एनर्जी लेवल सबसे कम रहेगा. तो अगर एनर्जी लेवल सबसे कम रहेगा, फॉर एग्जांपल मैं एक डेटा दे रहा हूं, जैसे कि मैं लिखूंगा सपोज माइनस. जनरली वो जो एनर्जी लेवल है वो माइनस में आएगा. यहां पे देयर विल बी माइनस आल्सो, बिकॉज माइनस इंडिकेट्स दैट द इलेक्ट्रॉन इज बाउंड टू द न्यूक्लियस. इवन इन ग्रेविटेशनल चैप्टर यू माइट हैव स्टडीड that minus sign आता है, where minus indicates that the planet is bound to some other planet, like that. So ये एनर्जी लेवल माइनस होगा. So suppose अगर मैंने बोला कोई एनर्जी लेवल, मैंने रैंडमली लिख दिया 13.6 इलेक्ट्रॉन वोल्ट, ये ग्राउंड स्टेट का है एनर्जी लेवल. ओके, तो मुझे ये चीज बताओ, क्योंकि ये मुझे पता है, ये आपको पता है, कितना एनर्जी लगेगा मुझे उस इलेक्ट्रॉन को फ्री करने के लिए ग्राउंड स्टेट से? मिनिमम एनर्जी कितना लगेगा फ्री करने के लिए, जिसको हम बोलते हैं आयनाइजेशन एनर्जी, या इसको बोलते हैं बाइंडिंग एनर्जी. अगर मैंने डेटा लिखा -13.6 इलेक्ट्रॉन वोल्ट, तो हाँ करेक्ट, प्लस 13.6 इलेक्ट्रॉन वोल्ट, ये मिनिमम है. इससे ज्यादा दे सकते हैं. अगर इतना दिया मिनिमम, तो आपका इलेक्ट्रॉन फ्री हो जाएगा, यानी कंडक्शन बैंड में चला जाएगा. दैट्स बेसिकली व्हाट इट मींस. ऑलराइट, तो यू कैन सी दैट सबसे ज्यादा नंबर ऑफ शेल्स होने के कारण, जैसे आप सबने बताया, यहां पे जर्मेनियम का जो एनर्जी लेवल है ये सबसे कम होने वाला है. तो अगर एनर्जी लेवल ये सबसे कम होगा, मैग्नीट्यूड वाइज आप देखो, इसको फ्री करने के लिए आपको इतना ही लगता है. इसको बोलते हैं बाइंडिंग एनर्जी या आयनाइजेशन एनर्जी कहते हैं. तो जिसका ग्राउंड लेवल का एनर्जी सबसे कम है, उस एलिमेंट में ग्राउंड स्टेट के इलेक्ट्रॉन्स को फ्री करने के लिए कम एनर्जी लगेगा. दैट मींस बैंड गैप आपका कम होगा. इसका मतलब है जर्मेनियम का बैंड गैप सबसे कम होना चाहिए. बैंड गैप शुड बी द स्मॉलेस्ट. उसके बाद सिलिकॉन का आता है बैंड गैप, ये स्मॉलेस्ट है. इससे कम ये है, और इससे कम ज्यादा ये रहेगा. तो ज्यादा बैंड गैप इंक्रीज होगा फ्रॉम जर्मेनियम टू कार्बन. ओके, इज दिस पार्ट क्लियर, शर्वरी? That why we can expect that the band gap of germanium is going to be minimum. Okay, so objective में ये पूछेंगे कि सिलिकॉन और जर्मेनियम में से किसका बैंड गैप कम है. That is linked with the number of levels. That's why I told you even before. याद रखो, दो है, ये सेकेंड वैलेंस शेल है, थर्ड है, फोर्थ है, क्योंकि इसका कनेक्शन यहां पे आ गया। और कल ये मैं वापस इस पॉइंट पे आऊंगा, तो देयर आल्सो विल डिस्कस द सेम थिंग कि what is binding energy, what is ionization energy, we'll discuss that part here. Okay, so that's what here also they have written here in your CBSE book, that ये जो second, third और fourth orbits में है, तो energy required to take out an electron, which is called as the binding energy or ionization energy, will be least for germanium. Why? Because of this formula that they have not written here, but it is because of this formula, which will be followed by silicon and will be followed by C. And that is the reason why they are saying that carbon is a this one insulator, क्योंकि सबसे ज्यादा एनर्जी कार्बन को लगने वाला है। तो ये अलग तरीका से ये बताया है, rather than talking about that the band gap is very large for carbon, वो तो हमने ऐसी स्टेटमेंट बोला था, बट अभी हम मैथमेटिकली भी देखते हैं ये चीज को कि कार्बन का नंबर ऑफ ऑर्बिट्स कम होने के कारण जो एनर्जी लेवल होता है वो बहुत हाई रहता है ग्राउंड स्टेट में, तो आयनाइजेशन एनर्जी बहुत ज्यादा लगेगा, and that is why carbon is an insulator. All right, so I hope now you can make the parallel between the energy band diagram and what you're going to study in modern physics. ये दोनों के बीच में relation becomes clear. So we will speak about extrinsic semiconductors. So what we'll do is that if the session ends, then we will not continue after that. All right, so till whenever the session is, I don't know whenever it is, we'll continue. So extrinsic semiconductor का मतलब है अगर आप impurities डालते हैं intrinsic semiconductor में, तो फिर हम उन सेमीकंडक्टर्स को कहते हैं एक्सट्रिंसिक सेमीकंडक्टर्स। ऑलराइट, सो देखो कंडक्टिविटी, जस्ट अ लिटिल बिट बैकग्राउंड, कंडक्टिविटी जो है इंट्रिंसिक सेमीकंडक्टर का है, ये टेम्परेचर पे डिपेंड करता है, वो हमने देखा है। टेम्परेचर जैसे ज्यादा बढ़ता है तो द electrons which are there in the ground state, they can get transferred to the excited state. और मगर फिर भी रूम टेम्परेचर में इसका कंडक्टिविटी सेमीकंडक्टर्स का ज्यादा नहीं है, ओके, इट्स नॉट टू हाई। तो प्रैक्टिकली इन टाइप के सेमीकंडक्टर्स का कोई वैल्यू नहीं है, you cannot use it as it is, it's of no practical use for us in electronics unless you improve their conductivity by making use of certain impurities. और सेमीकंडक्टर्स का एप्लीकेशंस आप देखोगे, the entire electronics is based on semiconductors. You start with diodes to transistors to JFETs to MOSFETs to all your ICs and everything, they are all made of semiconductors. So semiconductors is the heart of physics or a heart of electronics, sorry. So and this whole process is done by adding impurities. और impurity ज्यादा ऐड करने की जरूरत नहीं है, only few parts per million आपको ऐड करना है, और suitable impurity अगर आपने ऐड कर दिया तो कंडक्टर मैनिफोल्ड आप इंक्रीज करा सकते हैं। तो इनको बोलते हैं हम एक्सट्रिंसिक सेमीकंडक्टर्स। और इस प्रोसेस को जहां पे आप इंप्योरिटी को ऐड करते हो, इसको हम बोलते हैं डोपिंग। डोपिंग का मतलब है इंप्योरिटी को ऐड करना, इस प्रोसेस को बोलते हैं डोपिंग। और जो इंप्योरिटी आपने ऐड कर दिया, कुछ इंप्योरिटी एटम आपने ऐड किया होगा, उन इंप्योरिटी एटम्स को हम बोलते हैं डोपेंट्स, ओके, डोपेंट। और मटेरियल को हम बोलेंगे इंट्रिंसिक, नहीं तो डोप्ड सेमीकंडक्टर। All right, so these are just some few terms which we have to get familiarized with. So I hope that these terms have got into your head. So extrinsic semiconductor is a process of doping, where you dope or put some impurities called as dopants, and you are going to get a doped semiconductor or an extrinsic semiconductor. All right, and the number of impurities are not too much, you have to just put a few parts per million. So there are two types of impurities which you can put in intrinsic semiconductors, and depending upon the type of impurity that you put, you could get two types of semiconductors. You could get one type of semiconductor is called as N-type semiconductor, and N-type would mean that the number of free electrons is much greater than the number of holes. That's one type of semiconductor which we are going to get. And the second type of semiconductor which we'll see is when the number of free the holes is much greater than that of the electrons. And such type of semiconductors we will see will be called as the p-type semiconductor. So if you want to get an n-type semiconductor, the impurities which are going to add here are going to be pentavalent impurities. Now, why pentavalent? Why not hexavalent or something like that? Actually, when you are going to add this impurity, it is going to form some bonds with the silicon or germanium. So, जो atom के जो size रहेगा, that also has to be something similar. So, that is why you're taking the elements which are just one above the fourth. जो आपका सिलिकॉन है, कार्बन है, ये सब आपका टेट्रावैलेंट एलिमेंट्स है. ओके, तो टेट्रावैलेंट एलिमेंट्स में आप इधर पेंटावैलेंट इंप्योरिटीज ऐड करोगे जिसके फ्री इलेक्ट्रॉन्स जो आउटर मोस्ट शेल है वो 5 रहते हैं, नहीं तो ट्राइवैलेंट इंप्योरिटीज आप ऐड करेंगे जिसके आउटर मोस्ट शेल में 3 इलेक्ट्रॉन्स रहते हैं. तो कुछ एग्जांपल्स जो हम ऐड करते हैं पेंटावैलेंट का, वो है आर्सेनिक, एंटीमोनी एंड फॉस्फोरस. ये याद रखना है, ये 3 नाम ऑब्जेक्टिव में काम का चीज है. ये दे विल आस्क दैट इन चारों एलिमेंट्स में से कौन सा इंप्योरिटी पेंटावैलेंट इंप्योरिटी है, तो यू शुड बी एबल टू आइडेंटिफाई दैट. तो आर्सेनिक, एंटीमोनी एंड फॉस्फोरस, दीज आर द पेंटावैलेंट इंप्योरिटीज. And trivalent impurities are indium, boron and aluminum. Okay, so these are some of the standard impurities which are added in electronics. All right, so Meher, can we go ahead? Is it clear till here what is doping and which type of impurities you'll add? Now what will happen after you add the impurities, that we'll see. But till what I have written here, it's all right. Okay, so she's given the thumbs up sign, so we'll go ahead. So let's see now what's going to happen when you are going to add a pentavalent impurity first. So this is your pentavalent impurity which has displaced a silicon atom, occupied its position, formed the 4 covalent bonds with the 4 adjacent silicon atoms and 1 electron. Because it's a pentavalent, there are 5 electrons in its outermost orbit. This 5th electron is unbonded, it has no bonding, and therefore it is free, or we can consider it is donated to the entire crystal as a whole. Okay, and we will be seeing in some diagrams in future also that the ionization energy which is required to remove this electron and make it free electron, that means I'm talking about transferring it into a conduction band. Just because you have added it doesn't mean that immediately it's free. It has to get some energy from the room temperature, only then it will go to the conduction band. So it's something like this. If this is the conduction band level and this is the valence band level, adding of a dopant impurity like a pentavalent impurity produces some energy levels which are just below the conduction band at a very small electron volt value. ये जो value है ये तो 1.72 electron volt है silicon का, but that is very large at room temperature to get that much energy. So adding a pentavalent impurity, we'll see some diagrams in future also, will introduce a donor level, इसको बोलते हैं donor level, which is a few electron volt. कितना है देखो यहाँ पे लिखा है 0.05 electron volt. सिलिकॉन में इतना ही रहता है और रूम टेम्परेचर में बहुत ज्यादा हो गया वो. That is sufficient to transfer all these 5th electrons to the conduction band and thereby form a large number of free electrons. All right, so that's how you're improving the conductivity of an element like silicon or germanium. तो यहां पे देखो ये वैल्यूज भी मैंने दिया हुआ है. नॉर्मली जो इंट्रिंसिक सेमीकंडक्टर के होते हैं जो याद रखने हैं, आपको याद है कि जर्मेनियम का कम रहता है. जर्मेनियम में एनर्जी बैंड गैप इज 0.72 इलेक्ट्रॉन वोल्ट. आई थिंक आई हैड रिटन दैट एज 0.6 बिफोर. इट्स 0.72 इलेक्ट्रॉन वोल्ट. और सिलिकॉन में इसका वैल्यू है 1.1 इलेक्ट्रॉन वोल्ट. सो प्लीज रिमेंबर दीज टू वैल्यूज. और ये कम क्यों है ये हमने डिस्क्राइब किया है. ये इंट्रिंसिक में है, ये चीज मैंने इंट्रिंसिक में बोला है. और ये यहां पे क्यों लिखा है? क्योंकि ये जो एनर्जी है ये बहुत ज्यादा है रूम टेम्परेचर में, यहां से इलेक्ट्रॉन को यहां पे शिफ्ट करने के लिए। मगर अगर आप कोई डोनर इंप्यूरिटी को ऐड करते हो, पेंटावैलेंट इंप्यूरिटी को, तो ये जो इलेक्ट्रॉन है इसका एनर्जी लेवल कुछ यहां पे रहता है, विच इज वेरी क्लोज टू द कंडक्शन बैंड। इट्स ओनली सो मच फॉर दीज टू एलिमेंट्स, so it can quickly get free and you can have large number of free electrons. All right, Sharvari, is this acceptable? Okay, Omkar is saying explain again. So when you add a pentavalent impurity, 4 electrons form bonds with 4 adjacent silicon atoms because it displaces an existing silicon atom, and the 5th electron is free and therefore becomes a free electron which can be transferred to the conduction band. Okay, so in the case of your intrinsic semiconductor, this band gap was 1.72 electron volt. So the bound electrons here could not get sufficient energy to go here. But when you're adding some impurity, it creates a donor level or an energy level just below the conduction band, which is only 0.05 electron volt in silicon. And these electrons, which are not bonded to any of the atoms, they will easily get transferred at room temperature to the conduction band, thereby forming large number of free electrons. All right, Omkar? That diagram we will
Yes,
show
sir.
later of this donor level. That is not drawn here in this diagram. Okay, Omkar, is it clear? What is forbidden band? Forbidden band is only energy band. Forbidden band is this only. ये जो आप देख रहे हो ना 1.72 electron volt, इसको ही बोलते हैं forbidden band. It is a group of energy levels where you cannot have any electron because वहां पे कोई energy level exist ही नहीं करता. There are discrete energy levels ना. So this entire region is called forbidden band, where you cannot have electrons because there are no energy levels, allowed energy levels in this region. All right, Mohit? So forbidden band, energy band, all these are same meaning. Omkar, did you understand this part? What I told about
Yes, sir.
the number of conduction electrons increasing when you add a pentavalent impurity. There is no communication. Okay, yeah, ठीक है. So once you give an electron, what happens to the pentavalent impurity? Positive ion or negative ion? क्योंकि एक तो दे दिया उसने इलेक्ट्रॉन, तो एक इलेक्ट्रॉन का कमी है ना उधर. Okay, so that's going to be a positive ion. Okay, so all the pentavalent impurities are going to form positive ions. ये याद रखो. Pentavalent impurity corresponds to positive ion. All right, क्योंकि ये बाद में भी आएगा, ये डायग्राम्स हम बाद में ड्रॉ करेंगे, तो it will come up again. Now going up again, we have just written all these things. What we have written, explained that pentavalent doping is basically donating one extra electron for conduction, और इसलिए इन impurities को हम donor impurities भी कहते हैं. Donor, dopant और donor. Now specifically donor, ये सब डोपेंट इंप्यूरिटीज है, मगर डोपेंट में भी दो प्रकार के हैं. एक तो डोनर हो सकता है जो पेंटावैलेंट इंप्यूरिटी करता है, नहीं तो एक्सेप्टर भी हो सकता है जो हम देखेंगे एन टाइप सेमीकंडक्टर में. ओके, सॉरी, पी टाइप में. ये तो हमारा एन टाइप होने वाला है. तो देखो, डोप्ड सेमीकंडक्टर में टोटल नंबर ऑफ कंडक्शन इलेक्ट्रॉन्स, ओके, विल बी ड्यू टू टू सोर्सेस. कंडक्शन इलेक्ट्रॉन दो सोर्सेस के कारण है. एक किसके कारण? इलेक्ट्रॉन्स जो कंट्रीब्यूट होते हैं डोनर के कारण, और दूसरा इंट्रिंसिकली जनरेटेड फ्रॉम द वैलेंस बैंड. दो सोर्सेस है. एक तो इलेक्ट्रॉन्स यहां से ट्रांसफर होंगे और दूसरे यहां से भी ट्रांसफर हो सकते हैं. So there are two ways in which you can have conduction electrons in this type of semiconductor. Intrinsic और दूसरा है डोनर के कारण. और होल्स जो है इट इज ओनली ड्यू टू होल्स फ्रॉम द इंट्रिंसिक सोर्स, क्योंकि यहां पे जो बाउंड इलेक्ट्रॉन्स है एनर्जी लेवल बैंड गैप में हम अगर बात करेंगे तो ये यहां पे ट्रांसफर होने के बाद यहां पे एक वेकेंसी क्रिएट होता है, तो ये सिर्फ इंट्रिंसिक के कारण होगा, इसके कारण तो होल्स फॉर्म नहीं होगा. इसका मतलब ये हो गया कि इस प्रकार के सेमीकंडक्टर में number of electrons is greater than the number of holes, isn't it? Because electrons के लिए दो सोर्स है, एक यहां से और एक यहां से, मगर होल्स का एक ही सोर्स है और वो भी ये इंट्रिंसिक वाला है, दैट इज टेम्परेचर से, और वो वैसे भी कम ही है. मेन तो यही सोर्स है डोनर का, यहां से नहीं है मेन सोर्स. So that means that in this type of semiconductor where you add pentavalent impurities, the number of electrons become much larger than the number of holes. Intrinsic semiconductor में कैसा था? The number of holes were equal to the number of electrons. That is intrinsic semiconductor. And extrinsic semiconductor में दो possibility है, एक तो E is greater than H और दूसरा next वाला हम देखेंगे H can be greater than E. ये दोनों possibility है. और एक और चीज इंपॉर्टेंट पॉइंट यहां पे है कि नंबर ऑफ इलेक्ट्रॉन्स यहां पे बढ़ने के कारण रिकॉम्बिनेशन जो होगा होल्स के साथ वो भी इंक्रीज हो जाएगा. दैट इज व्हाई फर्दर द नंबर ऑफ होल्स विल बी फर्दर डिक्रीज देन व्हाट यू हैव इन इंट्रिंसिक. सो दैट दिस आर ऑल पार्ट ऑफ ऑब्जेक्टिव. यहां पे ये चैप्टर में आपको पता भी नहीं चलेगा कि कौन सा पार्ट का ऑब्जेक्टिव पूछ सकते हैं. एकदम छोटे छोटे पार्ट्स का दे कैन आस्क. So true or false, the number of holes in an extrinsic semiconductor is lesser than the number of holes in intrinsic semiconductor. True. Why? The reason is because more number of electrons are there, so the recombination with the holes will become more, and therefore the number of holes will get reduced further. All right, Shreya, is it acceptable? Okay, going up ahead, we have 6 minutes. 6 minutes में हम end करेंगे. Okay, so अभी because electrons are greater in number than holes in extrinsic semiconductor with pentavalent impurities, electrons will be called as the majority carriers. Okay, majority carriers, ये नाम हम लोग standard नाम है. तो they can ask, in pentavalent extrinsic semiconductor, holes are the majority carriers, true or false? So you have to be very careful about all the theory part. So pentavalent impurities mein electrons are the majority carriers, and holes, because they are less in number, they are called as minority carriers. And because electrons are more in number, that is why the term n comes here. But n does not mean that this particular extrinsic semiconductor is charged. That is not the meaning. The total number of positive charges is still equal to the total number of negative charges. All right. So they will ask a question saying that extrinsic semiconductor is not electrically neutral. True or false? It is false. Okay. It is electrically neutral only. The total number of electrons and holes, they are all equal. Total number of positive charges equal to total number of negative charges. Just because n लिखा है, इसका मतलब ये नहीं है कि वो negatively charged है. I mean, many of us after some time when we forget semiconductors, when we are asked the question that n-type semiconductor is negatively charged. If a true statement है कि false है, so everyone say true. Why true? Because they think n है तो negatively charged है. No. It is called n because electrons are majority. Only for that reason, because electrons are negatively charged particles, that's why यहाँ पे नाम दिया है n type. इसका ये मतलब नहीं है कि वो negatively charged है आपका semiconductor. All right? ये वाला part clear है? So Ne is very much greater than NH. ये आपका statement है यहाँ पे. Sharvari, is it clear? Can we go ahead from this part that these are electrically neutral? एक्सट्रिंसिक एज वेल एज इंट्रिंसिक, दोनों इलेक्ट्रिकली न्यूट्रल है. आपने इंप्यूरिटीज डाला है तो इंप्यूरिटी का जो पॉजिटिव चार्ज है दैट इज इक्वल टू द नेगेटिव चार्ज ओनली. Okay, you're not done any charging here in this place. Now going ahead to the next type of impurities. I don't know what is this about. Okay, this is about yeah, trivalent impurities. So dopant atom of the p-type material. No, actually this they don't tell all these things. What's written here? Holes are in addition. Okay, so basically when you talk about trivalent impurities, suppose you add trivalent impurities like boron, indium, aluminium and all these things. Trivalent impurities है sir. So यहाँ पे what's going to happen is that here your trivalent impurity is going to displace one of the silicon atoms. It's going to form bonds with the four adjacent silicon atoms, but one of the bond is empty. Okay, that's what you see here because it is having only 3 electrons in the outermost orbit, all trivalent impurities. So only 3 bonds are filled and 1 bond is empty. And that empty bond corresponds to a hole. And we know that holes can also contribute to movement of charges in semiconductors, where an electron thinking that grass is green on the other side will come here and hole will transfer here. Okay, so in such type of material, you will see that holes are going to be the majority carriers. So if you talk from the viewpoint of energy band gap diagram, when you add a trivalent impurity, it creates an energy level called as the acceptor level just above the valence band here. Okay, so all the electrons out here, they will all jump here to this acceptor level and thereby, cause holes out here. So holes are going to be the majority carriers here because so many different bonds are there of the impurity atoms, all of them contributing to a hole. And therefore, this type of material where holes are greater in concentration than the electrons is called as a p-type semiconductor. It does not mean that it is positively charged. Okay, now total number of electrons are equal to the number of positive charges. It only means that the holes are more than that of electrons. All right. This is also clear. We have only a minute left. Mohit, can we go ahead for the last minute? I don't know what is there on the next slide. But is this part clear here? P-type semiconductors means that we are going to add trivalent impurities which are going to cause a large number of holes which are going to be greater in concentration than the electrons. So I think that even if I start the next slide, we'll not be able to complete it. So we'll stop right here. So next Sunday, we'll continue with this topic of semiconductors and we will complete the section in such a way that after next week, next week I'm going to do in our regular lectures modern physics. So we'll be completing that and semiconductors part 2 will be starting next week. So by that time, next Sunday, we'll finish this topic, whatever they have studied in 11th. All right. So I think that's the plan up here. So we'll stop right now and we'll meet tomorrow.